Good afternoon. Today I'm presenting our first-in-man assessment of the Tau20 retromapping system, a novel atrial fibrillation activation mapping system. Activation mapping has proven instrumental in our understanding and management of complex tachycardias, and it's also been applied to atrial fibrillation, often in epicardial surgical mapping studies, and has demonstrated different types of activation waves in those studies. But whilst productive, these approaches all remain extremely labor intensive, usually requiring manual annotation of activations and isochrones. Atrial fibrillation presents unique technical obstacles that make activation mapping exceptionally challenging. First of all, most clinical activation mapping is predicated upon a stable cycle length that allows a fixed reference electrogram and window of interest throughout the entire mapping process. Secondly, standard peak detection algorithms used to annotate activation, like voltage thresholding, DVDT, and template matching, are also vulnerable to failure as electrogram morphology varies in atrial fibrillation. But most fundamentally, the rapidly varying activation patterns in AF mean that activation cannot be represented with a single static isochronal image, so it's necessary to select and visualize only key data. In order to address those challenges, we've developed the Tau20 retromapping system, which is a 48-channel recording and stimulation system with a novel activation mapping technology. The Tau20 retromapping system is an investigational medical device. It's an atrial fibrillation mapping system which is compatible with and runs in parallel to existing commercial 3D navigation systems with fixed electrode spacing catheters. You can see here the junction box, the console, and on the right the software interface with electrograms, and in the top right of the software interface, what we call the wave watcher with an activation map below that. Here are some examples from our recent validation work on this system over the past year. For the rest of the presentation, you will see the system being used with an Afocus 2 catheter, which is a 20 electrode double loop catheter. First, we validated in atrial tachycardia. In the top right of the user interface, you can see again the wave watcher. The spiral of yellow dots that you see represents the shape of the 20 electrodes that make up the catheter face. And when these light up, it confirms signal quality to the operator, which is a proxy for catheter contact and healthy tissue. And this is all necessary for the algorithm to detect clear activations. Below this, you can see an activation map, which shows the activations on the catheter face and which updates automatically. Red areas are early activations and blue areas are late activations. This activation map is generated immediately and updates in real time with each wave event as soon as the operator places the catheter on the atrial wall. Next, we have an example of validation in sinus rhythm with ectopy. The first wave here approaching the playhead is sinus rhythm, activating earliest at electrode 1, which will show up as red on the right of the activation map. And you'll see the system subsequently automatically detects ectopy and reverses the activation map for these events. So here we have more ectopy and yet another ectopic beat and a fourth ectopic beat. And then a little bit of time will reset, and then you'll see the sinus beat reverting to the original pattern, and finally one more ectopic beat. Now, although there are alternating patterns of activation, this is relatively easy to follow because it's slowed fivefold and also because it's a relatively simple pattern of activation. We found that at full speed, it's difficult for an operator to keep up with this, and especially with more complex combinations of activation patterns. And it is for this reason that we developed the retro map, which displays a smoothed dynamic average of all organized activation patterns in a given area. So looking at exactly the same recording again, now with the retro map in place of the activation map, you can clearly see two red dots simultaneously, one on each side of the catheter face. And this reflects the earliest activation of the dominant sinus pattern and the emerging pattern from the ectopy at the same time. Now, returning to the atrial tachycardia example, what you likely didn't realize is that this, in fact, isn't a standard activation map. It's also a retromap. And you can tell it's a retromap because it's updating live to show that smoothed dynamic average of all organized activation patterns. It's just less obvious in this example because, by its nature, atrial tachycardia is a more stable activation pattern. So in this case, the retromap is showing that all of the activation is originating from almost exactly the same direction, which is of course exactly what you would expect from an atrial tachycardia. Now, moving on to looking at the real core technological advantage of retromap with something much more challenging, induced AF. Here we can see the induced atrial fibrillation, which although relatively regular, actually has a changing activation pattern. And you can see how the earliest activation pattern on the retromap seesaws between electrode 4 and electrode 12 continuously to reflect the shifting activation pattern. And again, this all occurs without any setup, including reference electrogram or window of interest. And now you'll see at the end here, as the AF breaks spontaneously into sinus rhythm for 2 beats, the retromap reflects this instantaneously. Before we finish, I want to share a quick demonstration of the Tau20 retromapping system in clinical use to track down focal drivers of atrial fibrillation outside the pulmonary veins. We start on the posterior wall of the left atrium after pulmonary vein isolation, and looking at the retromap, the orientation of uniform waves shows some variation, but the earliest activation is centered on electrode 4 at the bottom of the retromap, which is highlighted on the 3D anatomy here. Under the hypothesis that uniform waves are emanating from a focal driver of atrial fibrillation, the operator moves the multi-electrode catheter in that direction, like so. So now we can see the catheter is in that new position, directly overlying the earliest site of activation. Now the retromap shows uniform waves are traveling in all directions, and the red area representing earliest activations covers the entire perimeter. The bullseye configuration fits our model for indicating that this is a focal driver of atrial fibrillation. In summary, activation mapping in AF presents unique challenges, but is also an opportunity to understand the mechanisms of this heterogeneous disease at an individual patient level. We've developed the Tau20 retromapping system, a novel tool to allow activation mapping in AF by automatic annotation and algorithmic filtering for uniform waves, before presenting a dynamic retromap of only these uniform waves to the operator. Our early work with this system shows interesting patterns of activation can be detected reliably, which change after PVI, potentially pointing to focal drivers of atrial fibrillation outside the pulmonary veins. We've secured the necessary approvals for a randomized controlled trial to test this hypothesis, which we've now begun.